Hey class, this is section 4.1, solving systems of linear equations in two variables. The first thing that I want to start off with is talking about what is a solution or what is a system. Okay, if we're talking about a system, we're talking about two equations in this case. So this first equation represents line 1. This second equation represents line 2. Okay, and if we're looking at line 1 and line 2, when we ask, is an ordered pair a solution to the equation? Is it a solution? What we're asking, so is the ordered pair a solution? What we're asking is if you plug the ordered pair in, is it true? Does it make a true statement? Remember that an equation is a statement. It says that negative x plus y is 2. So if I substitute the value of 1 for x and the value of 5 for y, right? If I substitute those values, is the statement true? Well, if I substitute 1 for x here and I substitute 5 for y, then I get negative 1 plus 5, which is 4. And we're saying 4 is 2. Well, that's not true. It's false. Okay, what does false mean? If you get a false value, that means that this point right here does not lie on this line. So the point x, y, whatever it is not on the given line. In this case, it's not on our line 1. Okay, so but if I plug in the 0.15 into the second equation, so if I substitute 1 for x here and I substitute 5 for y here, then I get that negative 3 equals negative 3, and that is a true statement. Okay, if this is a true statement, well, what does this mean? This means that the point x, y, whatever one we're testing, which in this case again is this one, it lies on the second line. So it is on the given line, line 2. Okay, so it's on this line. So if I were to look at the graph of this, or whatever it looks like, say like it looks like this. Okay, then the point negative 3, 3 is on that line. Okay, that's what that, the point 1, 5, excuse me. Say the point 1, 5 is on this line right here. So how can I tell then if it's false for this first one but true for the second one? Is it a solution to the system? Well, the system, it's only a solution to the system if it lies on both lines. So because it does not lie on this line, it's not a solution to the system. So no, this ordered pair 1, 5 is not a solution, because although it lies on this line, it does not lie on line 1. Okay, so if we plug in this next ordered pair, negative 1, 1, you can see here if I substitute negative 1 and 1, then I get that 2 is 2, and that's a true statement. So again, what does that mean? Well, a true statement means that this point right here lies on this line. Great, so we know that that point's on this line. Well, if I plug this into the second equation, negative 1 and 1, then I get that negative 3 equals negative 3, which is also a true statement. Remember, that means that that point lies on this line as well. Well, the only way that that's possible, that they're both true, both of these lines, because they're different lines, but they both came up with a true result. That means that this point is on both lines. So yes, it is a solution. So yes, the ordered pair, negative 1, 1, is a solution. And the reason why is because it lies on both lines, but the only way that it could possibly lie on both lines. So if you think about two lines that look like this, up here in this one, we're maybe talking about like this point. We're like, yeah, okay, so it lies on this line, but not on this one. But if it lies on both, it's the point where they intersect. And that is what makes it the solution. Okay, so is the ordered pair a solution? All it's asking is for you to plug it in, substitute the value of x and y, and see if does it make the statement true, okay? And it has to be both statements. Because if it doesn't make both statements true, then it's not a solution to the system. It's only a point that lies on one or the other line. Okay, so go ahead and pause the video and tell me whether or not -2, 3 is a solution to this system. All right, so this just means, again, if you're asked, is this a solution, means to plug it in. So plug in the values. So we're going to plug in -2 for x and 3 for y and see if this statement is true. -10 plus 9 is equal to -1. -1 is -1. This is a true statement. So I know for a fact that this point right here lies on this line. But that does not mean that it's a solution to the system. I have to plug in to the second line. So x is -2 minus 3, and that is equal to 1. -2 minus 3. Well, that is a -5. And so this does not equal, this is false. So this point right here lies on this line, but it is not a solution to the system because it's not on the other line. So the answer here would be no. That ordered pair is not a solution to the system. Okay, so understanding what a solution is very important in this section. Okay, so the next thing we're going to talk about then is what types of solutions we can get. So there are 3 possible solutions. And first we're going to look at them graphically. Okay, the 3 possible solutions we could get is we could get lines that actually intersect. Okay, well, what does that mean? Intersecting lines. Well, they literally will look like this. And these lines will intersect. And at this point right here, where they intersect, we will say that one point is the unique solution. There's only one. There is no other point in the entire XY coordinate system that would lie on this line. Okay, not a single other point that would lie on both of these lines here. Okay, so if they intersect, and we're not talking about perpendicular lines here. These can intersect at any angle. So if they aren't parallel or the same line, they will intersect. And where they intersect, that is where the solution is. Okay, that is how you find the solution. Well, what would a problem like this look like if I were to graph it? Well, intersecting lines, if I had x plus y is equal to 2, if this was my system, and 3x minus y is equal to -2, and I wanted to graph these. And I said, hey, well, what's the solution? I could visually look at this and say, well, it's the point where they intersect, assuming these lines do. Okay, so if I wanted to graph this first line, which I'm going to graph the first lines in blue, so my line 1 will be in blue, and my line 2 will be in green. Okay, so if I want to graph these, I'm going to use, for the first line, I'm going to use intercepts. I'm going to say when x is 0, this goes away, and y is 2. And when y is 0, this goes away, and x is 2. Okay, so I've got the point 0, 2, which is right here, and the point 2, 0. So this line looks like this. My line 1 looks like this. Okay, well, what about line 2? Well, I'm going to take line 2 and I'm going to solve for slope-intercept form because that's going to be the easiest here. So I'm going to get a negative y is equal to a negative 3x minus 2. I'm going to divide everything by a negative 1. And when I do that, I get that y is equal to 3x plus 2. Slope-intercept form says that this is the point 0, 2, and this is my slope here. So I know that the point 0, 2 lies on the green line, which happens to be this point right here. But then I'm going to go up 1, 2, 3 and write 1. And that is this line right here. Wow, that was a really pathetic line. But you get the point. Okay, so if I say, well, what is the solution to this system? You would go, hey, right there. They cross at the point 0, 2. And notice, they will never cross anywhere else. That's why these equations, or these systems, have only one unique solution. Okay, they won't have more than one. They won't cross ever again. Okay, so that is visually, graphically, an example of intersecting lines. Well, another possibility is that we could have parallel lines. Remember, parallel lines have the same slope but different y-intercepts. Okay, so we know that, but parallel lines could look like this, or they could look like this. Okay, so the point is that if you look at parallel lines, there's one fact that we know about them. They will never intersect. And because when we're saying, hey, what's the solution to this system, we're literally saying, oh, tell me the one point that lies on both of those lines. If you have parallel lines, if they never intersect, there is no point on this line that will ever cross this line. So here we will have no solution. Okay, what does this look like? Well, if I had the system y is equal to 3/4 x plus 1 and 3x minus 4, y is equal to 12. So if these were my lines, and again I'm going to graph line 1 in blue and line 2 in green so that we can clearly see them. So if these were my lines, this one is already in slope-intercept form right here. So I'm just going to draw out my graph real quick, and I'm going to say, hey, my ordered pair that I'm looking at is the point 0b, so this is 0, 1. So this line starts at the point 0, 1, and from there, my slope right here, it says go up 3, 1, 2, 3, and right 1, 2, 3, 4. Okay, same thing as going down 1, 2, 3, and back 1, 2, 3, 4. All right, so my line, my blue line, I'm infinitely better at drawing blue lines than I am at green, would look like this. Well, I'm going to graph this line 2 using intercepts because it's in the format to do that easily. So if I plug in 0 for x, this goes away, and then I would get that negative 4y equals 12. So to find out what y is, then I would divide by negative 4. So y is negative 3. Y is negative 3 when x is 0. That's finding my intercept. Okay, well, what about when y is 0? Well, when y is 0, this will go away, and I'll get that 3x is equal to 12. When I divide by 3, I get that x is equal to 4. Okay, so those are my two intercepts, the point 0, negative 3. So 1, 2, 3 here, and the point 4, 0. All right, so this line then is going to look like this. And if I could draw a perfectly straight line, you could see that these lines will never intersect. They're parallel when you draw them out on the graph. They're never going to intersect. Therefore, this system here would have no solution. Okay, the next possibility is that we could have coincidental lines. Coincidental means that the lines coincide. This word coincide right here, coincide. Coincide means basically that they're the same stinking line. Okay, well, what does that look like? Well, it's literally like if I was like, hey, here's my line, and I graph that, and then I'm like, oh, and there's another line, and it is the same line. Okay, so they coincide. And this literally means that every point on one line coincides with all of the points on the other line. So what type of solution would we get here? Because this is weird. So let's look at an actual problem here. If we had the ordered pair, or the solution, oh my goodness, the system, 2x plus 4y is equal to 10, and 2y equals negative x plus 5. Okay, if these were our two systems, and blue is going to be my line 1, and green is going to be my line 2. If I wanted to graph these, I would put them both in slope-intercept form. So looking at line 1 here, putting it in slope-intercept form, I would subtract the 2x because I'm isolating y. I would get the 4y is equal to a negative 2x plus 10, divided by the 4, and we would get that y, that's a 4, y is equal to a negative 1/2 x plus 5/2. Ooh, hate that already. Okay, so that's my line 1. Line 2 is just one step away from being in slope-intercept form, so I'm going to solve it for slope-intercept form. I'm going to divide by 2, and we can see that y is equal to negative 1/2 x plus 5/2. And if you look at these lines, you can see that they are exactly the same line. Okay, so if I were to graph line 1, my y-intercept would be the point 0 and 5/2. 5/2 is the same as 2.5, so I've got 1, 2, 3, 4, 5/2 here. And from here, I'm going to go down 1 and right 2, and down 1 and right 2. So this line looks like, oof, like this. Okay, but up here. Okay, so this is my blue line. And if I were to graph the green line, it is going to have the exact same thing. So it would go through this point here, and I would go down 1 and right 1, 2. And it would also lie on the same plane. So as you can see, you can't always tell by looking at the original equations that they're the same line, but when you put them in slope-to-intercept form, it's easy to see that. So coincidental lines, coincidentally, have infinite solutions because they don't ever intersect. They literally are the same line. So there's an infinite number of solutions. Well, what does this mean? Infinite solutions does not mean that every ordered pair that I could pull out of anywhere is a solution. So for instance, just like this, if I said, oh my gosh, it's infinite solutions, that means everything's a solution. Then I tried to plug in the point 0, 0. If I plug in 0, 0, then I get that 0 is equal to 10. Well, that is absolutely false. So if the point 0, 0 doesn't lie on this line, it is not a solution. So infinite solution does not mean everything is a solution. It just means that because this line goes on forever, and the blue line goes on forever, and the green line goes on forever, and they share every point on the line, there are infinite solutions, but not everything is a solution. So not all points or all ordered pairs are solutions. Okay, that's not what infinite solutions mean. It just means that there are an infinite number of ordered pairs that we could come up with that would satisfy both of these equations. Okay, so this is graphically what all of these look like. So now we're going to talk about a couple other words that you'll hear. The word consistent means that there's at least one solution. So if I were to look at these, my intersecting lines are consistent because there is a solution. Okay, again, it means that there is at least one solution. My parallel lines are not consistent. There is no solution, so it's not a consistent system. But coincidental lines are consistent because there is at least one solution. Okay, well, what does inconsistent mean? Well, inconsistent means that there's no solution, so we would call parallel inconsistent. All right, so what about independent? Well, independent means that each equation can't be algebraically derived from the other. So if I look at this equation, it's not the same to begin with, but I can use principles of algebra like we did here and make them the same. Okay, so these are not independent equations because they are the same equation. So what does that mean? Okay, well, that means that coincidental lines are dependent. Okay, they're dependent. But if you look at intersecting lines, I could put them in slope-intercept form and they wouldn't be the same line. So they would be dependent, or independent, excuse me, they would be independent. They are their own equation. They cannot be derived from the other by algebraically doing something. So if I put them in one form or the other, they're not going to be the same equation. They're independent. And these are independent equations as well because we know that the definition of parallel lines is that they have the same slope but different y-intercepts, which by definition makes them different equations. So we will have independent here as well. Okay, so that's how we define all of those. So we've talked about graphing wise, how you can find these solutions. You can literally physically see what they look like. Okay, so I think I'm gonna stop this video here, call it part 1, and then we'll talk about the 2 other types of equations